Good morning, everyone. In the previous class, we studied the concept of correlation, which helps us to understand the degree and the direction of relationship between two variables. Today, we are moving a step further from measuring the relationship to the predicting the relationship. That brings us a new topic that is known as regression analysis. Correlation tells us whether two variables are related and how strongly they are. But it does not tell us how much one variable will change when other variable is going to change. For example, suppose correlation between education and the level of income is 0.8. It means that they are strongly related. But the correlation cannot predict how much income will increase with one more year of education. That means along with the year of education, how much level of income is going to change. So the correlation give us only the association and not a quantitative prediction. So regression analysis was developed to quantify the relationship between the variables, and it expresses the relationship in the form of equation which can be used to take a or to make a prediction. So here the word regression was firstly used by Sir Francis Galton in 1886. He studied the relationship between the height of parents and children. Galton noticed something very interesting. See, tall parents generally have a tall children, but their children are usually little shorter than their parents. Similarly, short parents generally have a shorter children, but their children are usually little taller than their parents. So he observed that the height of children is regressed towards the mean height of their parents. In other words, what we can say, the children's height tends to move closer to the average height of the population. So not extremely as their parents. So regression means towards the mean. This tendency, see, extreme cases to move closer to the average in the next generation, which is called a regression towards the mean. So here a regression, what we can define as, it's a statistical tool which is used to estimate or predict the value of one variable or the dependent variable based upon the value of another variable that is generally treated as an independent variable. So in the case of a regression analysis, see, it is a statistical tool which is used to explain and predict the relationship between the variables. And in this method, see, we are generally used for estimating the value of one variable based upon the given value of other variable. And here also we are going to illustrate how the dependent variable changes in response to changes in the one more independent variables. So here we are also going to categorize what you mean by the dependent and independent variable. So here for a consider example of how the level of income which is depending upon the level of education. So we have two variables here. See, in this particular case, the dependent variable, that is here your level of income is depending upon your level of education. So why here? That means the level of income is considering as a dependent variable. That is the variable we wish to explain. Similarly, here the independent variable also we are going to consider, that is the variable which is used to explain the dependent variable. So in the above cases, see the example, that is the level of education is considered as the independent variable. Okay. Now, we are going to consider different types of regression analysis. See, regression can be classified on the basis of number of independent variables and the nature of relationship between the variables. Depending upon the number of independent variables, we can categorize regression as simple regression and multiple regression. Similarly, depending upon the nature of relationship between the variables, we can classify the regression as linear regression and non-linear, or it is also known as curvilinear regression. We will discuss one by one in detail. See, in the case of a simple regression, see, we are going to consider only two variables. That means one dependent variable and one independent variable. In the earlier cases, the level of income is depending upon the level of education. So we have only one dependent variable and one independent variable. And here, what we are going to do, we are going to predict the value of dependent variable from one independent variable, that is considering here in terms of x. So here the equation will be just like, it is y is equal to a plus bx or alpha plus beta x. So here y is the dependent variable and x is the independent variable. So consider one example, that is we are going to predict the income based upon the year of education. So the level of income is depending upon the year of education. So we have only two variables here, that is one dependent variable and one independent variable. So we know that a person's year of education increases, we can also estimate, or if you know the level of education, then we can also estimate the likely income which he is, or in near future he is going to receive. Okay. Now, as against the simple regression, we have also multiple regression analysis. See here, as against the simple regression analysis, it involves more than one independent variable, which is used to predict the dependent variable. So to measure, here we are going to measure a combined influence of several factors on one outcome, one independent variable. So we will have a one independent variable here and more than one dependent variable. Sorry, we have here only one dependent variable and more than one independent variable. Consider one equation here. It will be just like, y is equal to alpha plus beta 1 x1, beta 2 x2 up to beta n xn. N number of, independent variable can be considered. So here we have only y is the dependent variable and x1 and x2 are the independent variables. So here consider one example, predicting your level of income based upon your level of education, your level of experience and your age. So we consider three independent variables here, that is level of education and your experience and your age. So it will become a multiple regression analysis. So we can study here how each factors contribute to the income while controlling other factors. That is means we are going to consider here only three factors that will affect your level of income, keeping other factors are constant. Now, depending upon the nature of relationship, we can classify the regression as linear and non-linear regression. What do you mean by linear analysis? See, in the case of a linear regression analysis, we are going to study the relationship between the dependent and independent variables, which is straight line in nature, which means that changes in the y, that means changes in the dependent variable is proportional to the changes in the independent variable, that is here we are considering in terms of x. For example, y is equal to alpha plus beta x. This is a simple linear regression. Okay. So for example, if you are going to draw the graph of the linear regression analysis, then it will look like a straight line rather than a curve. It is a straight line curve because there exists a linear relationship or proportional relationship between the dependent variable and independent variable. So here the relationship between, for example, say the relationship between advertisement expenditure and the sales revenue. See here, these two variables are considering as a linear regression model, because as generally if your advertisement expenditure is increases, then the sales revenue is also going to increase. Now, consider the non-linear or curvilinear regression analysis. See, till now we have discussed the linear regression where the relationship between the dependent and independent variable are assumed to be a straight line, meaning that a constant rate of change will be appear in the case of a linear regression. However, in many of the real situations, the relationship between variable is not linear. That is, changes in x does not produce a constant changes in the y. So in this case, a linear regression, we assume a straight line relationship. That means a y changes at a constant rate when x is also going to change. But in non-linear relationship, see what happened here, it is not the case just like a linear relationship. The relationship may be a bent or curve, or it is it could rise quickly at the first and then slow. So it is not a straight line. So the relationship between the variable is not a straight line. In the straight line model, every times x increases by 1 unit, then y increases by the same amount or a fixed amount. So the slope will be the constant in the case of a linear relationship. So that is, changes does not produce, in this particular case, a curvy linear relationship, the rate of change is not constant. That means the changes in the x does not produce a constant changes in the y. See, imagine one example, that is how much you are going to spend the hours in terms of studying and their marks. So as usually we are assuming that extra hours of study will cause a large improvement, especially for getting a higher marks. After a point, extra hours don't help you much as you reach the saturation point. So that's why a non-linear pattern, it will create a non-linear pattern, or it is not constant. For example, consider some of the equations here. We have a quadratic equation, y is equal to alpha plus or a plus bx plus cx square. So it is a quadratic equation, and the graph of this quadratic equation will be generally a parabola, or it is the U-shaped, or it may be a inverted U-shaped model. Similarly, in the case of an exponential regression, see, where we are generally used when y increases or decreases at increasing rate. That means a change will accelerate or maybe decelerate over the period of time. So in this particular model, the situation may be growth, or maybe it may be a decay. So it here the curve will be, see, it will be shows a curved line rather than a straight line. Okay. So in the population, consider one example, that is the population growth. See, the number of population grow very faster and faster over the time. So that is an accelerating growth. Sometimes consider the example of a compounding interest. See, your investment increases slowly at first, but later it will grow further. It's been just like an exponentially as you earn interest on the previous interest. So that will be accumulated over the period of time. So that will create a non-linear relationship. Now consider here a population linear regression. See, in statistics, we often study the relationship between sample, but these samples comes from a larger population. See, the population regression line, which mainly represent the true relationship between the dependent and independent variables for the entire population. That means on an average, the dependent variable changes as the independent variable changes across the whole population. See here, here we are considering a equation for the population linear regression. This y is generally denoting for the dependent variable, that is, this is the variable we want to predict or explain. Similarly, we have here it is alpha, which is denoted for the population intercept. That means even if the value of y when x is equal to, see here, the A alpha is equal to the population intercept. This is the value of y when x is equal to 0. Then we have a beta, which is the population slope coefficient. Similarly, here we have an x, it is the independent variable, that is the predictor, or it is also known as explanatory variable. This variable will influence the dependent variable, that is y. Then we have random term, that is error term, that is e. It represents the other factors that are actually affecting y, that are not included in this particular model. So it capture the random variation, it is a measurement error, or it is the capture the omitted variable. Ideally, the average of E is considering as 0, that means no bias. Okay. Now, we are going to consider the assumptions of population linear regression. See, what are the various assumptions of population linear regression? See, the first one is here, it is linearity, which means that the relationship between the x and y must be a linear. That means the changes in the y is proportional to the changes in the x. If the true relationship is curved or non-linear, then the linear regression model will give a biased result. So we are assuming a linearity. The second one, the random error term means will be 0. The sum of EI, that means the error term, sum of error term will be 0. That means the average of all error terms should be 0, which means that the regression line is drawn in such a way that equally balanced above and below the observed data points. We'll show in the upcoming slides. Then the third one, it is homoscedasticity. Homoscedasticity means that, see, the variations of error term, the variations in the error term should be constant for all the values of x. That means if variance changes, for example, the error get larger as x increases, it is called a heteroscedasticity, which means that can be distort our statistical analysis or statistical test. So we are assuming a homoscedasticity. Then the fourth one, it is no autocorrelation. That means the error term should be independent of each other. That is, the error for one observation should not depend on or predict the error for another observation. The violation of this assumption, that means the autocorrelation, is common in the time series data where consecutive errors are related. So we are assuming here there is no autocorrelation. Then the fifth assumption, that is normality. The normality of the error term. Error terms are assumed to be normally distributed for any given value of x. See, this is very important for conducting especially the hypothesis test and construct the confidence interval. Because this will also necessary, because when we are considering a linear relationship along with the remaining assumptions, the normality is also very important. So these are the 5 most important assumptions of the population linear regression, and that are popularly known as it is classical linear regression assumptions. Okay. Now consider one example here. Here we are considering the various students and their entrance examination score is also given, and the cumulative GPA, CGPA is also considering here. We are considering here, see, X is the entrance examination score is the independent variable and CGPA is considering as the dependent variable. Okay. So here we should transfer the information of this particular table into a particular graph. See, because here the chairman wishes to, department chairman wishes to use the examination of scores that predict the success in the college or not, that he wants to check. We have placed here the CGPA and along with their entrance examination, whether their entrance examination score will predict the upcoming CGPA in the semesters. Okay. So along with the entrance examination score, we are also given their cumulative GPA. So now I am going to put this is same by using the scattered diagram plots. See, on the y-axis I am considering the CGPA. Generally we are assuming the dependent variable in the y-axis, and in the x-axis we are going to consider the entrance examination scores. Okay. So we are placed here CGPA on the vertical axis or y-axis and the entrance examination score on the horizontal axis. Now I am going to represent, see here, the various plots on the various pairs in the given graph. So if we have a dots are representing for the each pairs, and also drawing a particular line. This particular figure shows that a complete scatter diagram. The pattern of point result here because each point on the data from the table has recorded as a single point. When we view all these points together, we visualize a relationship. So here we have a positive relationship, representing a positive relationship we have done in this figure, and it is common. It is common to try, draw this line so that equal number of point lies on the either side of the line. That means we have a balance between the positive as well as the negative errors. Now, considering these points, this particular graph I am taking into this separately. See, we can understand that how it look visually through the diagram, showing how individual data points related to the population regression line. See here, the population regression model expressed here, y is equal to alpha plus beta x plus e, where y is the dependent variable, x is the independent variable, then alpha and beta are the coefficients. Here alpha is the intercept term, and in the y-axis we are considering the dependent variable, and on the x-axis we are considering the independent variable, and each point sets are plotted here, and accordingly we have drawn the curve which is representing for the best fit, or which generally we are considering that it is the best fit line. So each dots represent here the actual data point, and the red line, see, it is the population regression line, which give the expected outcome for the each independent variable. That means, for example, we are considering the example of an income and the level of education. See, expected income for the each level of education is also given here. So here, see, some of the dots are the above and some of them are the below the line. That is the random errors. These are the generally considered as the random errors, representing that other factors affecting the income besides the education. So in the vertical distance, see, the vertical distance between the points and the regression line error, which is generally representing, this is error. This is the error term. So the part of y not explained by, x. So some of the points are above the line, that means it is the positive errors, and some of them are the below line, which is the negative errors. So the regression line, it is positioned so that the sum of these error can be minimized. So here the line here it is showing that, actually average trend in the population, not a perfect fit, but at the same time best average relationship. Okay. Now, considering the estimated regression model, see, the main goal of the regression estimation is to find best fit data. But since we are rarely study the entire population, we are relying on the sample data to estimate that particular relationship. So here the sample regression line provide an estimate of population regression line. So here we have y hat, which is equal to alpha hat. I am representing it is hat plus beta hat x, where y hat, which is representing estimated or predicted value of y, and it is the estimated regression intercept, beta is the regression slope, and x is the independent variable. So here the population regression model is actually a theoretical, but at the same time the estimated regression model is considered as the empirical, or it is based upon the actual data. So the individual error term here, that is EI, that is mean of 0. That means even in the case of an assumption, we are put that the average of the sum of mean of the error term is equal to the sum of error term is equal to 0. The difference between the population regression and the estimated or observed value, actual value and the observed value is generally considered as your estimated value. It is considered as the error term. So error is nothing but it is the difference between y, that is observed value, and the estimated value here. Now, based upon that, we have a line of regression. See, what do you mean by line of regression? It is the line that is the best fit for this scatter diagram point or scatter data point, that is the average relationship showing the trends or the direction of the relationship between two variables, that is x and y. Let us consider we have a two variable, that is x and y, where y is the dependent variable and x is the independent variable. We will have a two regression lines. One is regression of y on x. That means the probable value of y for any specific value of x. If you know the x, then you can also calculate the value of y also. Similarly, as against the y on x, we have the second regression equation, that is x on y, which gives the probable value of x for any specified value of y. If you have the given value of y, you can also calculate or predict the value of x as well. So we have a two regression lines. See here, in this particular case, see, we have a two regression line. I am visually representing the two regression lines here. The first one, that is the red line, which is representing for the regression line of y on x, and this line, which is used to predict the value of y for the given value of x. That means here it minimizes the sum of squared vertical distance, that means error term distance, between each point and the line. Similarly, we have the regression equation on the regression line on x on y as well, and this is the line which is used to predict the value of x for the given value of y as well. Okay. Now the point of intersection, that is x bar and y bar. See, the two regression lines are generally different unless there are the perfect correlation between the variables. See, if the two variables are perfectly correlated, then these two lines are coincide. Otherwise, we have a two separate regression lines. So the point of intersection is generally considered as the mean value. So the key property of this line is that always intersect at the mean value of the variable, okay, which is represented here x bar and y bar. At the mean value, the both variables are intersect. So based upon the regression line, we have a regression equations as well. See, it shows that average relationship between variable. See, there are the regression equation, we are going to capture the algebraic expression or mathematical expression of the regression line. See, since we are said that we have a two regression line, see, we will have a two regression equations as well. See, the regression of y on x, that means here y is equal to alpha plus beta x, where y is the dependent variable and x is the independent variable. Similarly, see, consider here y is the dependent variable, x is the independent variable, and alpha is the intercept term, and beta, here it is beta or b, it is the generally considered as the slope. Similarly, we have a regression on x on y as well, that is x is equal to alpha plus beta y, where x is the dependent variable and y is the independent variable as well. But the remaining things, this alpha is representing for the intercept and beta is representing for the slope as well. Now, we are going to consider certain properties of a regression line. So, the first property says that both regression line pass through the mean point, that is x bar and y bar, which we are already shown diagrammatically. See, both line of the regression always intersect at the point representing, it is mean value of x and y. See, this is happen when we substitute x is equal to x bar into the regression equation. And this point this point is generally considering as a balancing point. Both regression lines represent average tendency, so that it's natural they intersect at the average of the both variables. Okay. Now, the second property, see, there are two regression line unless coefficient of correlation is plus or minus 1. See, generally there are two distinct regression lines, that is one is y on x and another one is x on y. But they coincide and become a single line only when the correlation coefficient is equal to plus 1 or minus 1. See, in the case if correlation coefficient is equal to plus 1 or minus 1, then the relationship between x and y is perfectly linear. Every data point lies exactly on the regression line, so both lines will be overlap. So if r is less than 1, the relationship is imperfect, so we will have a two regression lines as well. The closer the line, higher will be the correlation. See, the angles between the two regression line depending upon the strength of correlation. See, if correlation is high, that is it is nearer to the or close to the plus 1 or minus 1, then both lines are close together. If r is relatively or low or it is closer to the 0, then lines are far away from each other. So this means that stronger relationship, lesser scatter plots, and two regression line almost overlap. Okay. Then the fourth property, it says that the product of two regression coefficient, which is equal to the square of correlation coefficient, that is r square. If you multiply the coefficient of two regression coefficients, then it will leads to the r square. See, r square is generally considered as a coefficient of determination. This is a different concept which we will discuss at later stage. R square is the coefficient of determination which capture how much changes in the y, which is explained by the independent variables, that is x, that is captured through the concept of r square. Okay. Then the fifth property regarding the regression line, see, the regression coefficient have same sign as the correlation coefficient. That means both regression coefficients always carry a same sign as the correlation coefficient are. See, if correlation coefficient is positive, then both regression coefficients are also positive. That means as x increases, y also increases. If r is negative, that is if correlation is negative, then both regression coefficients are negative, that is x is increases, y is decreases. So these are the general properties of the regression lines. Now we have methods to obtain regression equation. So we have a different methods are there. We have a normal equations, We can derive the equation from deviation taken from the arithmetic mean, or maybe the deviation taken from the assumed mean also. So the line of regression, generally what we are already explained, that is the line of regression is the foundation for all the regression analysis. These methods for obtaining the regression equation we will explain in the next lecture. So we are concluding here. See, the concept of regression analysis which we are already discussed here, the line of regression is the foundation for all the regression analysis, and it provides not just as a visual representation, but also it represents a mathematical equation that is used to predict and interpret the nature of relationship. So the regression line provides a predictive equations that helps to forecast unknown values and understand how strongly and in what direction the variables are moving together. So let me conclude here with this lecture, and in the next lecture we will discuss what are the various methods to obtain the regression equation. Thank you.